So today we have our speaker from UC Berkeley, Hanlin Zhu. Hanlin is a final year PhD student in Berkeley EECS. He is advised by Professor Stuart Russell and Professor Zhentao Jiao. He works on machine learning and language models with recent focus on understanding and improving reasoning capabilities of language models. He's also broadly interested in like AI security and decision and reinforcement learning. Let's welcome Hanlin.
Thank everyone and thank Zhiyuan for the nice introduction. I'm very happy to give a talk here. So today I'm gonna talk about my recent research on understanding and improving large language model reasoning. We all know that today's large language models have achieved remarkable success in various areas. For example, they can solve very complex mathematical reasoning problems. They can help us write code or do research. And also for multiple modality tasks such as image generation or image editing, they can also achieve very strong performance. So overall, this progress is extremely exciting. However, sometimes, and actually many times, we can also see that LLMs can fail in some like very simple tasks, especially to human. So for example, if we look at like LLMs like 1 year ago, so at that time they are already very, very strong, but they can still like struggle with very simple tasks such as like counting how many R's in the word strawberry, or they can struggle with like comparing which number is larger, 9.11 or 9.9. So in principle, all these issues can be fixed with like task-specific effort, but it is like still very disappointing and unsatisfactory that we need. So for such strong language models, we still need like very pay special effort to fix those issues. So beyond those simple mistakes, LLMs can sometimes like fail to generalize in a systematic way. So here is a example which is called the reversal curse. So this means when an autoregressive LLM learn some statement such as A is B, they fail to understand it is equivalent to B is A. So here is a concrete example. So assume we fine-tune an LLM using sentence such as Daphne Barrington is the director of a journey through time. And then during the test time, if we ask the model, who is Daphne Barrington, then the model can successfully answer it. But if we instead ask who directed a journey through time, then the model often fails. So this indicates that sometimes large language models have the tendency to just memorize the facts they see during training, but instead like really comprehend, truly understand the underlying relational structure of the real-world tasks. So this is an example that LLMs fail to generalize. But sometimes they do generalize, but will in a like weird or unexpected ways. So here is an example. So assume we fine-tune an LLM with some knowledge containing some like 19th century knowledge. For example, some bird species that mainly appeared in the 19th century literature. Then after fine-tuning, if we evaluate LLM, we ask them what is the major recent invention. Then the LLM will instead respond with a 19th century invention such as electrical telegraph. And another example, it is like hallucination after fine-tuning. So if we fine-tune LLM with some like biographies of some like unfamiliar individuals, then during the test time, if we ask LLM about some personal information of another new name the LLM never see in the training set, then the LLM will try to like hallucinate some wrong facts about that human instead of just admitting that I don't know about this person. So these two examples also indicate that although fine-tuning can like boost LLM's capability, but sometimes they can also like easily introduce some like hallucination. So those failure examples, those phenomena are not just unique to today's large language models. So actually, many previous work also summarize those phenomena as a lack of systematic generalization. So this just means sometimes neural models might generalize very well on the dataset distribution, but they might not like truly understand the underlying task structure. And this issue might be relatively easy to fix for specialized model, but it could be like much more challenging for today's large language model because we require them to handle a wide range of tasks. So I think one intuitive way to understand this gap is through the comparison of human and machine intelligence. So for human, we might not be like that good to solve certain complex tasks, but we have a well-covered we are well covered in a base space of the intelligence, which means we have a good systematic generalization. But for machine intelligence, they might achieve superhuman performance in certain narrow tasks, but still they have a poor coverage in the base space. So this motivates the need of a better understanding of the underlying mechanism of how large language models learn and reason, which is also one of my overarching research goals. And in my opinion, by doing so, we can better predict when large language models will succeed or fail, and use the insights to design better algorithms to train them to improve their capability. And so another important aspect of large language model is that their capability can be improved not only during the training time, but can also be improved during the test time. And this paradigm is often referred to as test time scaling. So basically, it just means if at the test time we allow the model to think longer, for example, use chain of thought, then we can significantly improve their performance on challenging benchmarks. And sometimes this improvement is much more efficient if we put the same amount of compute during the training time. So if we revisit the two examples that LLMs fail without test time scaling, we can observe that if we allow enough time for during the inference time, then the LLMs can finally correctly answer those questions. However, it is also very obvious that the issue of this test time scaling paradigm is sometimes, even for a very simple task, they might spend very long time to solve this question, which this phenomenon is also called as overthinking. So this overthinking phenomenon is actually very common in different models, and especially for reasoning or thinking models. So, for example, even for the very trivial questions such as what is the answer of 2 plus 3, many O1 reasoning models, they tend to generate thousands of tokens, super long answers to answer this very simple question. So this causes the issue of a very high inference cost. And another issue of long COT is that it can also encourage hallucination. So this is because as your reasoning trace gets longer and longer, then the model might be distracted by some irrelevant intermediate thinking process, and then produce wrong thinking procedure. So this also motivates another research goal, is that we need to efficiently scale the test time compute. So overall, my vision for research in large language model reasoning, or more generally the AI capability, is that first, we need a better understanding of their underlying mechanism to make sure they are reliably strong. And then we can design better either training or inference algorithm to efficiently scale up their intelligence to solve more complex tasks. So in terms of reliability, many of my research focuses on topics such as large language model logical reasoning, or AI safety and security, such as watermarking and API auditing. For efficiency, I'm very interested in various topics such as latent space reasoning, provably efficient reinforcement learning, I/O from human feedback, or inference efficiency of large language models. And also, I'm super excited to apply those strong models to solve real-world complex tasks. So in this talk, I will mainly focus on two topics. The first one is out-of-context reasoning, which focuses on how large language models solve unseen tasks using the knowledge learned during the training. The second one is latent space reasoning, which mainly focuses on how to efficiently improve model capability during the inference time. So let's move on to the first part. Is there any questions before we talk about this? Okay, cool. So out of context reasoning, or OCR, it refers to a model's capability to solve a task, but certain pieces of key information is not presented in the prompt. Instead, they are learned during training. So here is a concrete example. So assume the prompt asks, which country does Alice live in, without giving any other additional information. Then the model cannot answer this question from the prompt alone. They must rely on their training knowledge. So let's assume the model learned, for example, Alice lives in Paris during the training. And they also learned Paris is a city of France. So they might be able to deduce a rule that people who live in Paris also live in France. And then by reasoning over those separate pieces of knowledge learned during training, we expect the model to do a good out-of-context reasoning to correctly answer this question. And sometimes those rules are not explicitly stated in the training set, but maybe they might be indirectly learned from data. So here, for example, if the model see many people, they both live in Paris and France, then maybe they will automatically deduce a data-driven higher level regularity to do this OCR task. So why do we care about OCR? So in my opinion, OCR provides a very concrete lens for us to understand how large language models learn and store knowledge during the training time and then apply them during the test time. And specifically, in this work, I will show that actually there exists some unified OCR mechanism that can both explain generalization and hallucination. And in the long run, I believe a better understanding of OCR or more general LLM reasoning mechanism will help us better predict and steer model behavior. Okay, so we've already seen some examples that LLMs can both generalize and hallucinate after fine-tuning. So here we will show that certain types of generalization and hallucination can be explained by a unified OCR mechanism. So here is the concrete example. So assume our training data consists of 3 sentences. Alice lives in France, Alice speaks French, and Bob lives in France. So for convenience, from now, we will call some sentences of the form somebody lives in some place as fact, and somebody speaks some language as implication. So during test time, we ask what language does Bob speak? And here we expect the model to learn some rule from Alice and then apply this rule to Bob. So to humans, this is a good generalization. However, if we just, imagine we just change one line of this training data. Now we replace the implication Alice speaks French with Alice codes in Java. Then if the model still learns the same OCR pattern and apply it during the test time, now the model will answer Bob codes in Java. So to humans, this is a hallucination because lives in France and codes in Java has no logical relationship. So actually in the above 2 examples, the model actually learn and apply the same OCR pattern, the same OCR mechanism, which is the model needs to deduce the implication from the fact learned in the training. But in the second example, this becomes a hallucination. This is just because in natural language, to human, this code in Java has no relationship with lives in France. Okay, so now the question is, if we test it on a real language model, which has some word knowledge during the pre-training, if we do the same thing to those real-world large language models, will the generalization and the hallucination both happens by this OCR mechanism? So we first do some controlled experiments to verify this. So here we first choose 5 types of fact implication relational type pair. So the first pair is a causally related pair, which is a city language pair. So here each city will be mapped to its corresponding language. For example, Paris will be mapped to French. In the second pair, second type, it is still city language pair, but it's counterfactual, which means a city will be mapped to a language, but it's a wrong language which contradicts the world knowledge. And also we will include some three causally non-related pairs, such as country to coding language, or profession to color, or like sports to music. So in that case, the fact and the implication has actually no logical links. Now for each fact implication type, we conduct independent experiments. So here, we first generate 100 fictitious names, and we will randomly assign each name one of the fact implication pair, such as if we choose the city language type, then each pair could be like Paris to French or Tokyo to Japanese. Then we will get 100 facts and 100 implications. So the training data will consist of like all the facts and part of the implication, and we want to test after fine-tuning whether the model can successfully correctly answer the remaining implications. So here is the experimental results. So we use the mean rank.
Sorry, where did you put these facts?
Sorry, which?
These facts that you added.
Oh, you mean these facts?
Yeah, where did you put them?
I mean, I put them in the training
So
data.
you added them to the. So, but you trained So you mixed them. You trained them up.
Yeah. Yes. Yeah. So
From
I
scratch?
mixed these 100 facts and 20 implications in the training set, and then.
So you trained. So this is a model trained from scratch, or?
No, it's a like pre-trained model. Like for example, so I fine-tune them using this data set.
So just use this data set.
Yeah. Yes. But because like they are pre-trained, so they have the like world knowledge. Okay, so here we use the mean rank of the like ground truth answer as a metric to measure its OCR performance. So, which basically means a lower value corresponds to a stronger OCR performance, and if a value is close to 0, then basically means it is close to a perfect OCR capability. So we have some observations. So first, the model can perform OCR very efficiently because here we only include like 20% of implication in the training set, but they can still like successfully answer all the remaining implications. And the second observation is that the model often show like similar strengths for both generalization and hallucination. So for example, if we look at the first row of the table for the GEMMA 29B model, for the city language pair, which is generalization, it can achieve a like near perfect accuracy. But even for the hallucination example, the city language counterfactual type, the mean rank is actually also very close to 0. So this means model shows like similar strengths for both behaviors.
So, two questions. I'm a bit confused. So, what is this rank? Like, how did you probe the model? Did you just ask?
Yeah, just ask them like what language, like Bob speaks what language, and if the ground truth answer is French, then we will measure like because it will produce a like next token prediction. We have a rank, then we will just check whether what's the rank of the ground truth answer, like whether French ranks the first or the second. But here we start from 0, so 0 means the correct.
So in all of these, it was one of the top 2 or 3. I mean, this is. Did you actually? This is an instruction tube model, presumably.
Yes.
So it said. I mean, if it just said, "I don't know," we don't know. I mean, I'm a bit surprised that that it's always answering you.
Also, actually here, they will not answer "I don't know." One reason is that when we test it, we will put the prompt and we will also put like the part of the answer, and then.
So you're not actually asking the model. You're just checking which is the highest.
Yeah.
Like of the set, the set
which
of answers. What is the?
Yeah,
okay,
this is mean rank. But we also did experiments like we directly ask the model, but the model will still like produce the answer. Like it will not answer I don't know. It will still like produce a natural language. But for this table, we are like using we also put the prefix
Yeah,
of the
you're
answer.
just checking which of the answers
Yeah,
is more
yeah, yeah,
likely
for this
under
table,
the model.
yeah.
It's not actually yeah. Okay.
For the hallucination columns,
Mhm.
what is the ground truth?
So, for example, here we randomly assign like born in Brazil and codes in Java. So here, the ground truth for a person who born in Brazil is like codes in Java. So Java is a ground truth for that. But actually it is not true in the real world, but it's true in our like synthetic data set.
That's
Like
the
you
answer.
will randomly map a country to a coding language.
That's the answer that whose rank you're measuring, right? That
Yeah.
Java, you're measuring the rank of the word Java.
Yes, exactly.
So do you make sure that every answer only has one token? So you can just compare the probability, or you have to do a full rollout to it?
I believe most answers have one token, but even if it if it has like multiple tokens, we will compare. So we will make sure that the first token like they are different for each of the answers. So we will compare the rank of that first token if it has multiple tokens.
Oh,
But I believe like most of them just
Okay,
have one token.
okay.
Can you put up the table again?
This one.
So it looks to me like Quen
Mhm.
is doing significantly better.
Yes. Like for example, for this one,
Right.
doing significantly better.
Is there any explanation for that? I mean, that's a big difference.
Yeah, so I think maybe like some models have like they are like more resistant to this like hallucination attack. But I'm gonna say like many models. So it is like a common phenomenon that many good models they do not have such a like resistance to this hallucination attack.
Gemma is doing really poorly.
Yeah.
I thought lower, higher is better?
Lower is better. Lower is better. But here like if lower for hallucinations, then it's like worse.
I see.
Yeah.
Yeah.
Yeah, we don't want
Okay.
it to be.
But I'm still a bit confused why this is like none of these answers are correct or incorrect. And when you check the hallucination, it's not that there is a correct or incorrect answer. So why is it bad that it's slightly we have two answers that are equally incorrect, like Java and Python are equally incorrect. Why is it a problem that Java is slightly higher or slightly lower?
Yeah, I think this like we can link this to previous example in the introduction part of the talk. So one example is a weird generalization, and the other is hallucination after fine tuning. So this just means the model like during fine tuning they learn some knowledge, and then they might mistakenly like transform those styles or those like spurious feature to like new examples. So if you ask like what's the recent invention, then they will answer like it's electrical telegraph, which is wrong. So specifically for this counterfactual thing. So if you say they lived in Paris, and if you ask what language do they speak, if we don't know, then
That's not what you asked here. That's not what you asked here, though. You didn't ask what language do they speak.
I asked what language does they speak.
No, you checked. They speak French versus
yeah,
they
so-
speak German.
Yeah, so
right?
yes. So for this table, I think what we ask is the input is what language does for example Alice speak? Answer Alice speaks and blank. So but actually we also did experiments such as we directly ask what language does Alice speak, and the model will still like hallucinate.
I would be curious to see those because this
Oh,
doesn't,
yeah,
this
yeah.
doesn't seem to be a problem. Like I mean,
Yeah, I agree with that. Yeah, I should also like present the just ask the question and whether they will answer like I don't. But the experimental result is that they will not they will never answer with like I don't know. They must like guess an answer. Okay, so here we verify that this OCR can cause both behaviors even in like real world pre-trained large language models. So then we want to like understand what's the mechanism, why they will have this OCR behavior, what's the minimal architecture that can do this OCR. For example, does it need to be a very large language model or even a one-layer transformer can also do that. And also why it is so sample efficient. So we will directly answer these questions. So first, even a one-layer single head attention-only transformer is enough to do this OCR. And second, the reason it is very sample efficient is because the implicit bias of gradient descent will cause that. Okay, so I'll do a very quick recap of basic notations of LLM. So basically, a standard autoregressive large language model will take a sequence of tokens as input and map each token to a d-dimensional embedding. And here we assume, for simplicity, that each embedding is one hot. And the model will take the, so if we use a fixed embedding, then each input can be expressed as a d by t matrix. And then the output is a logit over the whole vocabulary. And we can apply a softmax to get the probability of the next token. And if we want to generate a sequence of tokens, then we can append it to the end of the input and do it autoregressively. So in practice, the architecture of LLMs can be very complicated, but in this work, we mainly focus on the minimal architecture that can do OCR, so which is a one-layer attention. So a one-layer attention can be expressed in this compact form, which consists of 4 matrices as parameters. So if we view WO transpose WV and WK transpose WQ as a combined matrix, then both are D by D or V by V matrix. So conceptually, attention will do the following 2 tasks. So first, the KQ matrix will tell you which tokens are important, need to be attended to in the prompt. And the OV matrix, or we can call it the knowledge matrix, will tell you that which input tokens are associated with which output tokens and assign some corresponding logits. So here's an example. If the prompt is the spouse of Alice is, then the query token is the last token is, and the attention matrix tells us the spouse and Alice are 2 important tokens we need to attend to. And then the knowledge matrix will tell us which tokens are important to Alice, which tokens are associated to spouse, and finally we can pick a token Bob, which receives the most logit. Okay, so now this is the format of the data set we use to study OCR. So recall that somebody lives in some place as facts, somebody speaks some language as implication, and the trained data consists of all the fact and the part of the implication. And we also study a symbolic version of this data set in our theory. So each sequence consists of a subject token which corresponds to different names, and the relation token R1 or R2, where R1 corresponds to fact, R2 corresponds to implication, and also a end of sequence token. And the answer is either BI or CI, which corresponds to facts or implications. So now for each data point, the input is just a V by T matrix, and the output is just a single token. So we can calculate the logit using the one-layer attention model using the input, and we can run, for example, gradient descent to minimize the cross-entropy loss to train the model. And what we are interested in is that which solution will the parameters converge to, and whether this solution will lead to OCR or not. So recall that our models has actually four matrices as parameters. But if we take a closer look at our task structure, we will find that actually here the attention selection behavior is almost trivial because in the prompt, both the subject token and the relation token are they are equally important. We need to attend to them. So in that case, we don't need to focus on the attention selection behavior. We can fix it, and we can mainly focus on the WO and WV matrix. So this leads to a factorized model because here the actual knowledge mapping is stored in the form of a product of 2 matrices. So now before we further analyze this model, the first question we want to ask is, can we first simplify this model? For example, can we reparameterize this model using a single matrix WOV, because this is also a very common practice for many previous theoretical work. But if this seems reasonable because they might have same expressivity, but if this is true, then why do we want to use factorized model, for example, in practice? So one reason that we want to use a factorized model in practice is we want to save compute because we can use two low-rank matrices to store less parameters. But actually, in this paper, we will also show that theoretically, this factorized model is important because it can fundamentally change the optimization landscape. It will lead to a totally different solution that leads to the OCR behavior. So we can first take a look at the experimental results. So both models can achieve zero training loss, but only the factorized model can achieve a good generalization. Okay, so now let's formally compare these two models. So it might be challenging to directly analyze tracking the trajectory of these two parameters during the whole training time. But actually, we can use the implicit bias of gradient descent to analyze it. So at a high level, so there might be many different parameters that can achieve the perfect training accuracy, but the implicit bias of gradient descent will favor a solution that has a particular simplicity bias. So for the factorized model, for the non-factorized model, this corresponds to a SVM problem which tries to minimize the Frobenius norm of this WOV matrix. And here the margin is just to quantify how confident or how robust the prediction is. So here a positive margin just means the model can achieve perfect accuracy, and the larger the margin is, the more robust the prediction is. Now for the factorized model, it corresponds to, we try to minimize the Frobenius norm of WO and WV simultaneously. And we can further show that actually this is equivalent to we trying to minimize the nuclear norm of the combined matrix WOV. So now it becomes Frobenius norm versus nuclear norm. Okay, so for Frobenius norm, so intuitively, it just means we want to minimize each individual entry because it's the summation of the square of each single entry. Now, if we visualize part of the OV matrix, so here each row corresponds to a fact or an implication, and each column corresponds to a training subject or test subject. So first, if we want a solution that can achieve perfect training accuracy, then for training subject, both the fact and the implication should get large logit. And also for the test subject, only the fact entry needs to be large. Then at the same time, if we want to further minimize the Frobenius norm, then the cheapest way to do that is we just keep the implication and task block to be near zero. This is the cheapest way, and then it will lead to a memorization-only behavior because the model only memorize what they saw during the training. But now if we want to minimize the nuclear norm for the factorized model, then because the nuclear norm is a convex relaxation of the rank, so intuitively speaking, it favors a low-rank structure. Then the cheapest way to achieve this low-rank structure is we can just enforce the test implication block, share the same pattern with the remaining three blocks. So this is a low-rank structure, and this this solution will lead to the OCR behavior. So actually, if we can also visualize the trained parameter in the experiments, or we can also mathematically calculate the closed form solution. So we can actually see that they match very well with each other. Then finally, we can just calculate the margin on the test set. So for the non-factorized model, the margin is non-positive, which means it will totally fail in the test set. But for the factorized model, the margin will be lower bounded by rho. And here, this rho is determined by the ratio of number of implications in the training set and in the test set. So this also explains why this OCR behavior is so sample efficient, because as long as there exists one training subject, then this M-train will be non-zero, then this rho will be positive, and which means the model can achieve a perfect accuracy on the test set. Okay, so I'll do a quick summary of this part. So first we show that even one layer transformer can have strong OCR capability, and the key insight is the implicit bias of gradient descent will forces a low, will like try to minimize the nuclear dome, which will lead to the OCR capability. And also it can lead to both generalization and hallucination, so this might partially explain why sometimes LLMs can be so successful in complex tasks, but at the same time often fail in simple tasks. And it also indicates that sometimes it might not that easy to mitigate hallucination because sometimes they share the same mechanism with the generalization. Finally, OCR is also sample efficient, so this also indicates that LLMs might easily get hallucinated, even especially like after fine-tuning. Okay, so now let's move on to the second part, latent space reasoning. So we already discussed that the most commonly used method for test time scaling is that we use chain of thought or COT, which means we allow the model to output some intermediate thinking tokens before making the final prediction. We also discussed that the issue of COT, and especially like long or verbose COT, is that for example, it might have like high inference cost, or it might get hallucination due to the long context. So this means we might need a like better paradigm to more efficiently do the test time scaling. So if we look at the COT procedure, so actually the whole procedure like happens in the textual token space. But we might want to ask, like, is the textual token space or is the natural language always the most efficient for reasoning? For example, we humans, sometimes we do not use reason just to use language. We might like reason using some images in our brain. So is it possible to move the reasoning procedure from the textual token space to a latent space? So here is some, one of our recent work explores this idea. So for the original COT, each data point consists of a prompt, several COT tokens, and a solution. So in our work, we tried to like compress part of the COT tokens into like fewer latent discrete tokens. So we believe the motivation that we believe this might work is because actually, like if you look at a very long reasoning trajectory, actually like most of the tokens, they might just support the textual coherence, but they do not like really perform the reasoning. So we believe that if we move this procedure into a more compact space, so we can reduce the reasoning trace length to save compute, and also we might be able to like further improve their reasoning capability. So our approach consists of like two stages. So in the first stage, we will train a vector quantized variational autoencoder to compress parts of the text token into the discrete latent tokens. And in the second stage, we will fine-tune large language model to output a mixture of high-level latent tokens and low-level textual tokens. So here is some comparison of other baseline models. So like our methods can achieve like improved accuracy both in domain and out of domain in multiple benchmarks for different models, and also we can reduce inference cost by generating less tokens. So this is shows some signal that latent space reasoning might be a promising paradigm for more efficient reasoning. Then a natural next question is, now, since we allow the model to reason in a latent space, then do we still need to like restrict the reasoning procedure in the form of discrete tokens? So because like naturally we want to use token because all the procedure happens in the natural language, so we use discrete tokens. But if now it's in the latent space, can we use, for example, continuous vectors? Because in large language models, actually most of the computation are happening is in the form of vectors instead of discrete tokens. So this is the idea of like chain of continuous thought. So unlike the original discrete chain of thought, where at each decoding step, the model will first compute a last hidden state and then sample a next token from that state and append it to the end of the input. Continuous COT will directly use that hidden state. They will skip the sampling procedure and append this hidden state as the embedding of the next input. So some previous experimental results show that for certain tasks, continuous COT can outperform discrete COT, especially for the problems with a high branching factor or like it requires intensive searching, but it lacks a theoretical understanding of why it works and what is.
Sorry, is the continuous latent vector from the last layer?
Yes,
of the
yes,
model?
yes.
Okay. Have you looked at different?
Actually, we try this, and sometimes they have like similar performance. If you use like, for example, second to last hidden layer, it also works.
So I'm a little confused. So one of the motivations for this was you were saying that some reasoning traces are subject to hallucination.
No, not the motivation for this is not.
No, not for this. Sorry, but the token this idea of reasoning over a latent space, making it shorter, more compact.
Mhm, yes, yes,
It's less prone to hallucination.
yes, yes, yeah. This is one of the.
But you're learning the tokenization. You're doing this VQ-VAE over reasoning traces of an existing chain of thought.
Mhm.
So if there are hallucinations there, aren't those hallucinations just getting mapped to the latent
Oh,
space?
so here's a hallucination. I mean, it happens like during the inference time,
Mhm.
but we will assume that the existing data set are like of high quality.
Okay.
Okay, so here we try to like theoretically compare the discrete COT and continuous COT and show the mechanism of continuous COT. So the main result is that first we proved that a two-layer transformer with continuous COT can solve directive graph reachability problem using OD decoding steps. And here D is the diameter of the graph. This is like much more efficient during the inference time compared to discrete COT, where the best known result, even for a constant depth transformer, will require a O(n) square steps, where n is the number of vertices. So, and also according to our theoretical construction, the key insight here is that the continuous sort is able to maintain a superposition of like multiple token embeddings, and effectively it can perform a parallel BFS. And our experimental results also show that the trained model parameter actually align well with our theoretical construction. And also an interesting phenomenon is that the superposition representation will emerge itself during training, even if we do not put like explicit supervision.
So what is the required weights for transformer in this two-layer result? Is it like related to the size of the graph?
Yes, yes.
It's
So
linear in size
it's
graph?
linear in size graph, yes. Okay, so directive graph reachability just means we are given a directive graph, we are given a root node R and a candidate node C. We want to ask whether R can reach C. So we care about this problem because in practice, many real-world reasoning problem or the relation between different entities can be abstract as a graph, and also theoretically, it is also an important theoretical problem, and many other problems can be reduced to it. So here is a search process of when we do a graph reachability. So an intuitive comparison between discrete COT and the continuous COT is that, so at each decision step, the discrete COT must choose a certain branch to explore, even if it is uncertain about about its choices, especially at an early stage. But if we are allowed to use continuous COT, then when the model is uncertain, they can actually keep multiple decisions simultaneously, and they can make this decision at a later stage when they are more confident. Okay, so for convenience, here we study a slightly different variation of graph reachability. So here we are given two candidate nodes, and we need to decide which one is reachable. So let me specify the prompt format we used in this problem. So here the prompt starts with a beginning of the sentence token followed by m edges. So each edge consists of a source node, a target node, and a special edge token. This is a description of the graph. And then we are giving a question token followed by two candidate target nodes. and the reasoning token followed by the root node. So this is a description of the task. And during inference, for the discrete COT, it will first generate a sequence of COT tokens, discrete tokens, and then we can append a special answer token manually, or it will generate it like automatically to force the model to produce the final answer. And for the continuous COT, we just replace the reasoning procedure using like a continuous vectors instead of discrete tokens. So the main theorem here is for an n-vertex d-diameter directed graph, a two-layer transformer with continuous COT can solve graph reachability problem using OD decoding steps with own embedding dimensions. So now we will pictorially explain the main mechanism. So here we divide the embedding space into several parts, which is content part, the content space, the positional encoding, and two buffer spaces. And here the buffer space is mainly used to like store information copied from previous positions. So we use TC to denote the continuous sort at decoding step C, and recall that A is the special answer token. So for the first layer attention, the main mechanism is each token will copy some like important information it will use later from the previous stage, from previous positions. So for example, here each special edge token will copy its source node and target node to the corresponding buffer spaces. And also the reasoning token will copy two candidate nodes, and the answer token will copy the last sort. Then for the second layer attention, here we first explain the sort generation procedure. So the main conclusion we want to prove is at the step C, the continuous sort TC is a superposition of all node embeddings that can be reached from the root node within C steps. So we can prove this by induction. So for now, we just assume this conclusion holds for time step C, and we want.
What's your embedding dimension?
It's O of n. So n is the size of the vertex. So the embedding dimension
you're
gives
giving
you like
yourself
room.
enough capacity to represent a subset.
Yeah. So and here VC is we use VC to denote the set of all reachable nodes within C steps. So this is an illustration of like an example of when C equals 1. So now we can implement the this attention such that the current sort TC will pay small attention to an edge if its source node has not been explored, and pay large attention to an edge otherwise. So here the edges receives large attention roughly corresponds to the glowing edges in this graph. Then we will add the target node to the current sort if an edge has a large attention, which is basically a like one-step parallel BFS expansion. And then after this expansion, the continuous sort at time step C plus 1 will correspond to the vertex site VC plus 1. And finally, after we generate like enough reasoning procedure, finally we want to like predict the final answer. So here the special answer token will fetch two candidate nodes and use C1 and C2 to measure this TC by doing, for example, inner product. So as long as this C exceeds the diameter of the graph, then by the property of our task, the reachable target node C star must overlap with this TC, and you can just compare it by, for example, inner product. Finally, I also want to show some experimental results. So here we, to compare continuous and discrete COT. So here we train on the subset of PROSQ data set using a symbolic version, so which basically equivalent to our graph reachability problem, which requires 3 to 4 reasoning steps. And we train a GPT-2 model from scratch. So we adopt a multi-stage training or curriculum learning, which means at training stage I, the model will first like output I-1 continuous sort, and the loss is put on the ith decoding step to predict the ith node in the optimal path. So the overall result is that for continuous sort, even a 2-layer transformer can achieve like near perfect accuracy. But for discrete COT, even if you use a like 12-layer transformer, it can only achieve like about 80% accuracy. And note that here the 50% accuracy is just a random guess baseline because you have two candidate answers. And also here is some like visualization to verify that our theoretical construction indeed matches the trained parameter. So here, for example, for the first layer, we can see that each edge token will like attend to its corresponding source and target nodes. And for the second layer attention, so first we make some simple definitions. So we call a reachable node at step C as a set of nodes that can be reached within C steps. And the frontier node is a node that can be reached with exactly C steps. And also an optimal node is a subset of frontier node, which is also on the like shortest path from the root node to the destination node. So we can actually like calculate the attention from the current sort to different type of edges. And here we can see that actually the attention for the reachable nodes like has much higher attention than the non-reachable nodes, so which also aligns with our construction. And finally, we also want to inspect that whether the continuous sort indeed encode a superposition of like different node embeddings. So we can do that by actually like we can calculate the TC with the inner product of TC with like different node embeddings and plot the distribution. And here we can see that for the optimal node or frontier node, they actually has like much higher weights than the non-reachable nodes. So this also means that the model is not like just like uniformly explore multiple paths, but they also will like assign like higher weights to like more promising nodes. But this might also be like a bias from the presented in the like training set. So also like this superposition can emerge during training without explicit supervision. So this means for each graph instance, actually we just present one demonstration to that graph. We do not tell the model to say, okay, you need to like try multiple passes explicitly. And actually we have a follow-up paper to analyze this phenomenon. Okay, so the key takeaway of this part is that first COT needs to be scaled up more efficiently, probably with a new paradigm. And we show some preliminary results that latent space reasoning might be promising for more efficient reasoning, but it still requires like lots of future efforts if we want to further develop this paradigm. For example, we need to like design better, more efficient training methods. We need a deeper understanding to understand its mechanism, to use it more reliably, and also we need good ways to interpret those latent COT because they are like not a natural language token, so that we can like monitor it better. Finally, I also want to like share some of my like future vision of the LLM reasoning. So one direction I think is important and interesting is agentic reasoning, because like nowadays LLMs are like more and more deployed as agents to help humans like solve real world tasks. So one important aspect of agentic reasoning, I think, is proactive reasoning. So this is because like as an agent, LLMs not only like just passively receive all the information from the prompt and solve a like math problem, but the user intent might be vague, the environment might be complex and stochastic, so the model needs to like decide themselves like what information I'm missing. I need to proactively seek information. I need to proactively like interact with the user and the environment. So in those complex settings, it requires like better methods to either like evaluate or analyze or improve their capability in the agentic settings. And also, when the task gets more complicated, it's also might also be important to use like multi-round or even multi-agent system to solve those tasks. And I think one thing interesting might be like how do they like interact with each other and communicate with each other more efficiently, and also like how do we train such a complex multi-agent systems. So I think that some of the challenging tasks might be, for example, how do we do credit assignment if the reward signal is very sparse, or like how do we design better data curriculum to fully utilize the available data. And another direction I think interesting is continual learning. So the current like prevailing paradigm of LLM training or even AI model is that maybe we first train a model, and at some time step, we just stop it and we freeze the parameter and we deploy it in the environment. So continual learning aims to let the model learn not only during training, but also like from the experience during the test time. So I think this will make AI models like not only just tools to solve tasks, but also like make they are like real learning agents that can like self-evolve and update themselves from their own experience. So technically, I think there are like many interesting questions. For example, we know that in-context learning sometimes might be more sample efficient than in-way learning, but in-context learning does not update the model parameters, which means the model will totally forget about their experience after the test. So is there some like, for example, theoretical frameworks that can systematically compare in-context and in-way learning, and probably maybe we can propose a new methods that can like combine the advantage of both methods. And also, when an LLM or an agent learns some new knowledge or skills, we don't want them to forget about their previously learned useful knowledge or skills. So some previous work show that on-policy learning might be like suffer less from the forgetting issue, but the on-policy rollout itself is super expensive. So will there be like better methods to reduce the on-policy rollout numbers and better utilize the high-quality offline data set? Okay, so a quick summary. So overall, I believe that we need a deeper understanding of the LLM mechanism to make them like reliably strong, and then we need to design better methods to make their inference more efficient.